I've given you examples with the temperature sensor, the pressure sensor, or measuring refractive index, or directly measuring physical change in length. But you could also think of, what if I wanted to do imaging and I wanted to image a biological sample. So, on the left here you have an image of some cells. Okay? So, these are cells. Now, you can see that this image is very hard to see the cells clearly. Right? And we talked about what makes a good image several classes back. I'd shown you this picture of the India Gate under fog. Right? What was it we said that distinguishes a good image from a bad image? The visibility, the contrast. Right? So, you can see here, you can make out that there is a cell, you can even make out some of the structure within the cell. So, you know there is something there, but the contrast between the cell, so this here, and the structures within the cell and the region surrounding the cell is very poor. So, this image is not a very good image. And if you are using this image to help make a diagnosis, is there some disease present? Is the person responding to some medication? Has the cell structure changed? Is this a cancerous cell or not? Is there malaria? Is it AIDS? I need to have very clear pictures. So, this picture doesn't have good contrast. In the case of the India Gate picture, it didn't have good contrast because of the fog which was scattering the light. Otherwise, you would have had a very strong reflection from the building, and from the regions around the building there was nothing, you don't have a reflection, and that is what created the contrast. Here you don't have a contrast because the refractive index of what we want to image, that is the cell, and the refractive index of the medium around the cell are very, very similar. The difference between these refractive indices is small. So, whatever change is happening to the light, say this image was taken in a microscope where light passed through the sample. Whatever difference or change happened to the light passing in the medium around the cell, a very similar change is happening to the light traveling through the cell. And therefore, there is not much difference, and therefore, we don't see that. So, there are many microscopic techniques which somehow, now the point is, if there was zero difference in what was happening in these two regions, there would be nothing I could do. But there is a slight phase difference between the cell and the region around the cell. It's too small for our eye to make out, but there is a small phase change. And if you can enhance that or use the fact that there is some difference and enhance that difference in some way, you can then make this a clearer picture. So, there are many microscopic techniques which somehow extract that phase, and here I am just showing you an image of something that has been done using what is called phase contrast microscopy. Okay. So, we are not going to go into the details of what has been done, but the image on the left was taken with a regular microscope. It is called a bright field image, and the image on the right has been taken with a phase contrast microscope. What I will tell you is that the phase contrast microscope uses the fact that you have light scattered because of the structure, because of that small phase difference, and you have light that travels through the other surrounding medium, and if you somehow take the scattered light and introduce a phase, additional phase there, and then interfere these two beams. So, you are using the phase contrast microscopy uses interference and therefore enhances the phase differences within your sample. Okay? So, the image on the right then is this enhanced image. You have taken whatever small phase differences are there and used interference to enhance those phase differences, and you can see the effect of doing so. And suddenly it becomes much more clearer, and there's much more detail. And of course, it's obvious that the phase contrast image is going to be a much more useful image for you to extract information out of. Okay? So this is just one example of where you could use interference. Okay. But how do I extract phase? We are still, all our detectors are only measuring intensity. They are not measuring phase. So if I keep saying we'll use the phase gives us this information. But how do I get the phase? Okay. So that's the question you should all be asking. Okay. So let's look back at this equation. Okay. So if I assume I have two beams interfering, then I have the intensity. And again, I'm always writing this just like as I, but remember I can always be more specific and say it's I of xy. That means that there is an intensity variation. There's a different intensity at every point on the beam, on the interference pattern. And with our sensor, we're able to capture that variation. We can't capture phase directly, but of course, every pixel of the sensor is going to measure the intensity lying on that pixel, and it need not be all the same, it will vary. Okay? All I'm able to measure is this intensity I of xy. But buried in that intensity is this I naught and this gamma, where I naught is nothing but the bias intensity, which is the sum of the intensities of the individual beams that were interfered, and gamma is something called the contrast or the visibility or the modulation depth, which is this function over here. So it's again a function of the intensities of the individual beams. Okay? So I do not know I1 and I2. I do not know delta. That's the phase difference between these two beams. All I know, and I know this because I can measure this with a detector, is I, this I here. So buried in this is I naught, gamma and delta. And I naught and gamma are functions of the intensities of the independent beams. Okay? If you were somehow able to ensure that the two beams were of equal intensity, I can reduce this equation, right? Then your gamma will reduce very simply to 1 because I1 is equal to I2. Okay. But in general, I will use this expression for the modulation depth and this expression I1 plus I2 for the bias intensity. Okay. What is the modulation depth? What do you think the modulation depth is giving me? What information? Sorry? Gamma is the modulation depth, so it's multiplying the cos term. Right? So maybe I didn't follow your answer. What's the maximum value that the modulation depth can have? It can have a maximum value of 1. If I1 is equal to I2, it will have the value 1. For any other ratio, it is going to be less than 1. And in fact, if one of these intensities is 0, what happens? If one of these is 0, that means there's no interference. That means the intensity of one beam is 0. I'm not interfering two beams. The third term in that expression, remember your interference expression was I1 plus I2 plus this cosine term. That comes because of the interference. So if I remove one beam, of course I don't have that interference term, and the intensity is just going to be the intensity of the individual beam. Okay? So 0 is not of interest to us. We always are looking at the case where you have two beams. But it can happen that the intensity of one beam is much lower than the other beam. Right? Why could that happen? Well, we are creating two beams, but now we are looking at a specific application. So we are saying one beam acts as the reference beam. I need interference. I need interference because interference is the way by which I extract phase. So, I am putting in an extra beam there just so that I can have that interference happen. One beam is the reference, the second beam is the beam that carries the information I am interested in. So, that beam is either travelling through a sample or getting reflected off a sample. That is the way by which I get that information off the sample. Now, when it transmits through a sample or reflects off a sample, it should not be hard to imagine that the intensity of that beam is going to fall quite a bit, right? If the sample is not very highly transmissive, even when it reflects, it's not a mirror-like reflection necessarily, right? Your sample could be rough surfaces. So, there's a lot of light going off in other directions. So, some light is what you capture. So, the intensity of the object beam is usually weaker than that of the reference beam. Now, this expression here is telling me the highest value of modulation depth I can get is 1. So, and gamma is what multiplies the cosine term, right. So, that is what is giving me my fringes, right. These are my fringes over here. This is an example of the fringes between two beams. In order for me to see those fringes clearly, I want this modulation depth, the difference between the maximum and the minimum here, to be as large as possible, right. I could have fringes where this is the, right. Okay, I remember these, it should be periodically spaced. I could have with the same period fringes like this. Right. Which one has a larger modulation depth? The green one has the larger modulation depth, right? It's maybe it has a depth 1 or close to 1. Now, if you were looking at fringes, which one would you see clearly? You would see the one with the larger modulation depth. So, this is the low frequency. So, if the low frequency, this is the low intensity. So, if the low intensity and the high intensity values are almost similar, that's when the contrast goes down. I can't tell the difference between them. There is a difference, but we aren't going to, our detectors are not going to be able to tell the difference. In order to tell the difference, the minimum intensity and the maximum intensity should be as wide or as far apart as possible. In other words, I want as large a modulation depth as possible. Ideally, I want the modulation depth to be 1 because that's the best I can get. So, when will I get a modulation depth of 1? If the beams have equal intensity. So, I really want the two interfering beams to have equal intensity, and if I had one beam reflect off a sample, and because in the process of reflection the intensity dropped greatly, how would I improve my interference? What could I do? I don't really have much control on the object beam, right? It is reflecting off the sample is what the sample is. Right? In fact, the whole idea is to measure what the sample is. I don't want to manipulate the sample. So, if I want to improve the modulation depth in my interferometer, is there something I can do, or I just have to live with the visibility I get? Sorry? Surprisingly, yes, because you always think of I must improve things, I must increase things. If I want to increase modulation depth here, you would actually lower the intensity of the reference beam. You want it to be closer in intensity to the object beam. So, you might actually throw away power in order to increase modulation depth. Could you think of anything else you could do? Think of the setup. Let's say I had a setup like this. This is source, beam splitter, so mirror, and I'm drawing, and my sample is, or this is not a mirror, let's make this the sample and detector. So, this is not a Michelson interferometer because it is not retracing paths. So, the light is travelling like this, the beam splitter is sending it here, and the mirror has been aligned to send it like this. It is of course optically path length matched and so on. So, one thing you said is lower the intensity. How would you do that? Or let me ask the question differently. How would you lower the intensity of the object beam? Exactly, you could change the beam splitting ratio. That could be one way, or I could put a filter in this arm that cuts the intensity here, but the filter is less efficient because there I am actually throwing away the power, whereas if I change the splitting ratio of the beam splitter, I am sending more power to the sample, which is making the sample beam higher intensity and less power to the reference beam, which means it might end up being equal intensity to the reflected beam, right. So, having a beam splitter of a different splitting ratio is good. There is a reason I did not draw the Michelson, because in the Michelson, what is the difference in the Michelson? You have the beam splitter, and then you would have this, and you would have your sample here, mirror here, and then they come. Why didn't I draw the Michelson? Why is changing the beam splitting ratio in the Michelson not really going to serve your purpose? You go through the beam splitter twice. So, if you say 40, 60, this beam goes 40 and this goes 60, on the return this will go 40 and this will, right. So, it does not help you, right. So, the Michelson is not necessarily the best to use if a beam splitter of a variable splitting ratio is not very good with the Michelson, but if you are not retracing the path, then you can use that. Okay. So, here what the images I have shown over here are some interference patterns. So, the image over here may be taken with two beams generated from a helium neon laser. So, that is why you have this red color. Now, they are both interference patterns, but they are not exactly the same, right. The one on the left seems to have a constant period. Fringes are slightly thicker in the middle and there is some difference, but the period, that is the distance from the center of this fringe to the center of this bright fringe to the center of this and to the center of this, is constant. Whereas, if you look at the fringes over here, there is a variation. Okay. So, this is an experimental image, this is a simulated image. So, you do not have the absolute dark here, but basically they are the same. You have regions of constructive interference and regions of destructive interference, right. And from one constructive peak to another constructive peak is what I call the fringe period, and the image on the left has a constant period, whereas the image on the right does not have a constant period. What do you think could be the cause for this? What could be interfering here and what could be interfering here? Remember, yesterday what did I say? Think of your interference fringes as tracing the paths of constant phase difference. Just like a isobar or isotherm is a graph that gives you constant temperature, constant pressure, right? An interference pattern, the fringes are indicating regions of constant optical path length, right? So, what could this have caused this image? What could have caused this image? You do not have to think about, do not go into the type of beam, but if you were to think of the two wave fronts that are interfering, what would the difference be between those two wave fronts? Maybe make it easier for you. Look at this Michelson interferometer that we have drawn here. Okay. if I consider that I have a beam of a certain width, okay, so I have a beam that of a certain width traveling, this reflects off the beam splitter, goes to the top mirror and comes back. So the returning beam from this mirror is this, right, it's traveling like this, is after the beam splitter. It's a plane wave, let's say I have plane waves. So its wavefront is going to be this plane surface here. So if I draw the wavefront of the beam that is coming back from the mirror M, this is the wavefront of this beam. Now let's say I have, this is also a mirror. Part of that beam gets split at the beam splitter and travels straight on to this mirror. It gets reflected, it comes back, and it also is a plane wave. So its wavefront also looks like this. Do you agree? Okay. Yes? What do you think the fringes will look like now? What's the path length difference between these two beams? Pardon? Path length, yes, you're right. In the sense, if I trace one beam, it travels this distance, it travels this distance, it travels back this distance, and then it travels this. Okay, I've said, let us assume all of that has happened. Okay, so let's say beam 1 has traveled a path length, optical path length OPL1. That takes into account all this double distance. And beam 2 has traveled a optical path length 2. And having each traveled this path length, they have arrived at the detector here with wavefronts as I have shown over here. Okay, so it takes into account the entire path length that is traveled. I'm drawing the beam splitter as if it doesn't affect. It also has a thickness, it also has a refractive index. So we have taken all of that into account. Okay, and we're taking a very simplistic picture. We said I have a plane wave incident and the plane wave stays a plane wave through all of this, and now I have these two plane waves that come and hit the detector. And I'm drawn them the way I have drawn them in this image here. Right? What do you think the interference pattern is going to look like? What will you see on the detector? Let's say I have a camera. What will you see? You will not see anything. I mean, that's not correct. You will see something. You will see, as he said same as source. So you will see a uniform intensity. Why? You don't answer yet. Why would you see a uniform intensity? When do you see interference happen? I'm also assuming that OPL1 minus OPL2 is less than the coherence length of your source. So the conditions for interference are set. We're not violating that. But as he says, if I assume everything is perfectly aligned and the wavefronts are as I have drawn them, you will just see a uniform intensity across that camera, as if one beam was incident on the. There's no path length difference across laterally. When do I get fringes? The fringes here, you're saying this region constructive interference happened, here destructive interference happened. That means a path length difference between the two interference beams is not the same everywhere. If you have the same path length difference everywhere, then over here you will just see the same intensity, right? In order to see a path length difference, I need to have a spatially varying path length difference. So in this case, what you will see is a uniform intensity. So the result will be a uniform intensity. If I could somehow get the plane waves to be like this, Then there is a spatially varying path length difference. That means in some places the difference is going to result in constructive interference. In another place it may result in destructive interference, in another place constructive, and then I get fringes. I can't get fringes if the path length difference is everywhere the same, right? How would I achieve this? What would I have to do to my interferometer to achieve that? How? Change the sample arm? How do I change the sample arm? I am saying the wavefront that was, if everything is perfectly aligned, the wavefronts coming from these two mirrors are parallel to each other. And now I am saying have one wavefront have a tilt with respect to the other. The wavefront is nothing but the beam that has come off those mirrors. So if I want to change something about the wavefront, what's my control to do that? Sorry? Why will changing the refractive index change the tilt of the wavefront? Or change the refractive index of what?
The medium from the beam splitter to the detector.
If I change the refractive index here, I affect both beams. Both beams travel through that region. So the overall result is no change at all, right? Both the beam coming from the reference arm and the sample arm are traveling in this region. Any change I do here affects both the beams equally.
Uniformly, is slowly varying from the same to.
Whatever I do, even if I do a slow variation, a gradual variation, a spherical variation, a paraboidal variation, it affects both beams. If I want to have a difference, I have to affect one beam and not the other. So I don't ever work in this space. Change the? Okay, but I'm asking you, you're getting the point, you have to change one arm, but why refractive index? I have a wavefront. So you go back to your beam theory. We are not doing anything different from what we are doing here. These could be Gaussian beams traveling through. If I wanted to change, a Gaussian beam is traveling like this, and I wanted to travel like this, is your first response change refractive index? Huh? How would I change? I have a beam. You're getting confused, I think. Just think of your Gaussian beams. I want to change the direction of travel of a Gaussian beam, of any beam. If I want to change direction of travel, tilt the mirror. So all you would do is, in the original setup, these two mirrors are 90 degrees to each other. I'll introduce a small tilt. So when I say perfectly aligned in a Michelson, if I want to see fringes, it does not mean the mirrors are at 90 degrees to each other. There must be a tilt. It has to be a very small tilt. But there has to be a tilt, and usually it is quite impossible to set the mirrors at 90 degrees. So if you are assembling it, you're going to invariably have a tilt, right? I will ask you another question later. What is the problem if the tilt is too large? Okay, but so think about that. But right now, in order to get a tilted beam, basically if I say the wavefront is like this and I want the wavefront like this, what I am asking you is, how do I tilt the beam? How do you tilt the beam? You tilt a mirror. So instead of having the mirror as shown, if I had one of these mirrors slightly tilted like this, then the beam that is reflected is going to be, if I tilt it too much, it doesn't retrace, it has to still come through that beam splitter and come. So it's a small tilt, right? And then I will have, so now you could consider you have one beam, this is the untilted beam, and then you have the tilted beam, and it's only in this region you will see fringes. Otherwise you just have uniform intensity, okay? So let's go back to my original question. What could cause this fringe pattern now? We have already answered it. If I have one wavefront like this and one wavefront like this, how is the path length difference varying? It's a linear variation. So I would expect that if constructive interference happened at some point or some line, at some distance away, the next constructive interference is going to happen. So that's the period. And that is just going to repeat because the optical path length is varying in a linear way, right? So periodically the fringes or the locations of constructive interference would happen. So you can imagine that this is nothing but the interference of two tilted plane waves. Now in the second image, the fringes don't have a constant period. The period itself is changing, right? So let's say my reference wavefront is this. What do you think the second wavefront could be that could cause this interference? Again, when I ask that question, what you should be asking yourself is, how is the optical path length changing? And if the optical path length is changing in this way to cause this picture, what beam would give me that kind of optical? I have to draw something here. So that when you look at the interference between what I've drawn here and what I've drawn here, it gives me this pattern. Now, what I've drawn now is some random squiggle. Do the fringes below look like they randomly places this constructive interference, and is it random? It's not. So it's unlikely the beam interfering with the plane wave is some randomly carrying phase, right? It has some specific behavior. Gaussian is, if I'm, you have to be very careful when you say Gaussian. All of these could be Gaussian beams. Gaussian is intensity. Okay, be a little more specific when you say Gaussian, because Gaussian, you have to be specific. Why? Because we are interested in what's the phase. When I ask you what's the wave that's interfering with the plane wave, I'm really asking you what's the phase of that wave. And the Gaussian beam, I can't say the phase, right? If you say Gaussian, you have to say, do you mean at the waist, far away from the waist, right? Because the phase is different everywhere. If I say plane wave, I don't have to say that, because the plane wave has the same phase behavior everywhere, right? But if you say Gaussian, you have to tell me where of the, which part of the Gaussian. Okay, so but we typically don't generate wavefronts with Gaussian phase, right? So I want you to use all the optical terms you have used. We have wavefronts. You are talking about a variation like this. What can give us a variation like that? Think of a more general shape. Spherical. That's why when I said, you said Gaussian, you could have said Gaussian far away from the waist is kind of spherical. Right? So yes, a spherical wave. So if my wavefront, the second wavefront, was something like this, then this is not a linear variation in optical path length anymore. The optical path length is increasing faster as you go further away from the center, right? And therefore the fringes are coming, the places where the constructive interference is happening closer each time. And so the fringes come closer and closer. Right? Now, I'll ask you a question I asked you some time back. With a Michelson, in order to see fringes, you should not have your mirrors perfectly at 90 degrees to each other, because then you just have two parallel plane waves coming and you have a uniform intensity. It is I1 plus I2. So it's more than the intensity of a single beam, but you don't see that interference, okay? In order to tilt one plane wave with the other, we said we introduce a small angle to the mirror. Now we'll see that when I have a varying path length, and here the variation is not constant, it's not linear, you can see the fringes start coming closer and closer. Keeping all of this in mind, I'm asking you, if I tilt the mirror too much in a microcell, what I might not see fringes. When I say too much, I'm not talking a large angle. I'm not talking such a large angle that the returning beam does this and doesn't even come back the right way. I'm not talking about that. Let's assume that it still hits the beam splitter and still comes, and there is still an overlap between beams. Okay, I'll only have interference if I have an overlap between beams, right? So I'm not talking about the case where I've tilted the mirror so much that the object and reference beams don't even overlap. There is still overlap. But if I have a large angle, I may not see interference again. Why? The fringes will be too close, my detector may not have the resolution to see them. Okay, you can see that these fringes are easier to see than these over here. This is a simulation mind. So if you were doing an actual experiment, there's going to be some noise in your system and you may not see the fringes in this region at all.